Hello everyone, how are you all? I hope you all are fine and safe. Well, again, welcome back to Quantum Mathematics. I am Aman Gupta and welcomes you all to my new video. And as you guys might have an idea about what we are going to deal with this and like what we are going to deal with in this video. So, let me tell you that firstly. We are going to derive the Euler's Mascheroni constant, that is this small gamma, with the help of this integral, that is the integral from 0 to infinity of e to the negative x whole multiplied with 1 over 1 minus e to the negative x minus 1 over x dx. So yeah, we are going to do that, and yeah, it's very good. Like I would place this constant on the second place as one of the best constants. Obviously, not second, but third maybe. Obviously after pi and e. Okay, so yeah, I think we should begin, and we are going to tackle a lot of things through the journey. Like in this journey, we are going to tackle a lot of things. You will get to know about all the stuffs, and again, I will tell you everything in detail. I'll explain you everything in detail. Okay, so let's begin. So first of all, I'll assume that our target integral, that is I equals integral from 0 to infinity of e to the negative x times 1 over 1 minus e to the minus x minus 1 over x dx. So this is our target integral, and basically let me tell you, from this integral we have to reach up to this thing, the infinite series as n goes from 1 to infinity of 1 over n minus ln n plus 1 over n. So, and basically this is one of the representations of the Euler's Mascheroni constant, although there are multiple representations of it. But for now, we are going to tackle this only integral, right? Okay. So let's just let's do multiply this inside the parentheses, and let's just take the common denominator. So yeah, we are going to do all the stuffs. So when we multiply it inside the parentheses, so this becomes e to the negative x over 1 minus e to the negative x minus e to the negative x over x dx, right? Okay. And for this rational number, or for this fraction, I'm just going to multiply and divide with e to the x to neutralize this numerator. So this becomes integral from 0 to infinity of, when you multiply e to the x with this number, so this becomes 1, and when you multiply inside the denominator, so this becomes e to the x and minus 1 minus e to the minus x over x dx, right? Okay. And then just so I integral from 0 to infinity, I'm just going to take, like, I'm just going to do, like, what do you call it? Yeah. So we are going to take the common denominator for this parenthesis, right? So how are we going to do that? So for that, this becomes x minus e to the minus x times e to the x minus 1 over x times e to the x minus 1 dx. So that's what I'm talking about, like that's what I was talking about, to take the common denominator, right? And that's how we do that. Let me just erase this. Actually, I just wrote it quite bigger way. So yeah, I hope you guys have noted down. Okay, so let's take that integral from here. So integral from 0 to infinity of x minus e to the minus x e to the x minus 1 over x times e to the x minus 1 dx. Now I integral from 0 to infinity of x, when you multiply e to the negative x with e to the x, so this becomes 1. And when you multiply e to the negative x with like negative of e to the negative x times negative of 1, this becomes plus e to the negative x over x times e to the x minus 1. Right. Okay. So now we are going to just have a look at this part of the integral, like the numerator part. Okay, so we are just going to convert it into an infinite series, and how are we going to do that? Okay, just have a look. According to Maclaurin series, e to the x is k equals 0 to infinity of x to the k over k factorial, right? And if I'm just going to replace x with negative x, so this becomes e to the negative x equals the infinite series as k goes from 1 to infinity, from 0 to infinity, of negative 1 to the k x to the k over k factorial. I hope you don't have any kind of problem with this, guys. Okay, next, let me just write down this again here. Not x but negative x as k goes from 0 to infinity of negative 1 to the k x to the k over k factorial, right? So I'm just going to write down the first two terms of this infinite series. So this becomes, when you plug k equals to 0 inside this this function, so this becomes 1. This is going to be 1, right? And then when you write the second, when you write k equals 1, so this becomes negative of x, right? And then we are having the infinite series as k goes from 2 to infinity of the same stuff, negative 1 to the k x to the k over k factorial. Okay, so I'm having e to the negative x equals 1 minus x, this one, plus this sum, and like I'm just gonna add x both sides, and then along with subtract 1 both sides. So that becomes e to the negative x when you add x plus x and subtract negative 1, and when you add here x, so x cancels out, and when you add negative 1, so plus 1 and minus 1 got cancelled out. So eventually you're gonna have this infinite series only, that is negative 1 to the k x to the k over k factorial. So I hope this is one of the best representation of your, well, yeah, this one, right? So yeah, or maybe we can just do something better. So e to the negative x plus x minus 1 is also represented as the sum as k goes from 1 to infinity of negative 1 to the k plus 1 x to the k plus 1 over k plus 1 factorial, right? So that's what, let's just replace this thing with our numerator in our target integral. Let's do that. Okay. So our target integral becomes integral from 0 to infinity of 1 over x times e to the x minus 1 times the infinite series as k goes from 1 to infinity of negative 1 to the k plus 1 x to the k plus 1 over k plus 1 factorial dx. So that can be written as integral from 0 to infinity, the sum from k equals 1 to infinity of negative 1 to the k plus 1 x to the k plus 1 over x times e to the x minus 1 times k plus 1 factorial dx. Or maybe we can write this as taking the infinite sum and all the terms independent of x outside the integral. So this gonna gives us right this one and like negative 1 to the k plus 1 and over k plus 1 factorial are independent of x, so they are gonna taken out, and inside the integral we are gonna have x to the k plus 1 over x times e to the x minus 1 dx. So this is yeah, and now you would say that this is really complicated, this looks ridiculous at first, right? Yeah, you're right somewhere, but we're going to simplify it in a manner that it's gonna eventually give us something better, right? Okay, so this is what we have, and if you look closely, it's like the numerator is written as x to the k times x, so this x and this x getting cancelled out, so eventually you're gonna have your I, that is our target integral, equals the sum as k goes from 1 to infinity of negative 1 to the k plus 1 over k plus 1 factorial, and the integral from 0 to infinity of x to the k over e to the x minus 1 dx. Have a look at this one. Okay, let me tell you something. Do you know that integral representation of zeta function, zeta of s? Do you know about that, guys? If you don't know, let me tell you that. So integral from 0 to infinity of x to the s minus 1 over e to the x minus 1 dx equals gamma of s times zeta of s. So this is the integral representation of the zeta function in terms of gamma and an infinite integral. Or more precisely, you can say that this is very important, but along with that, this one is also very important. Integral from 0 to infinity of x to the s minus 1 e to the zx minus 1 dx. This becomes gamma of s times zeta of s over z to the s. This is just the modified way of writing this one. When you plug z equals 1, so this becomes z, and eventually you're going to have this only. So these two things are very important. Please note that down as fast as possible. And if you don't know about zeta function, so Riemann zeta function is the infinite series of 1 over n to the s, where n, no, not n, but your s is the real part of s should be greater than 0. So that's the condition of the Riemann zeta function. Please note that down, this is very important, guys, and I hope you can relate it with that. Everything is getting matched in our integral, but when you see s minus 1 equals k, so s becomes k plus 1. So this means when you plug s equals k plus 1, so they're gonna have this integral becomes this one only, and on the other side this becomes the gamma of k plus 1 times zeta of k plus 1, right? So basically this part is gamma of k plus 1 times the Riemann zeta of k plus 1, and this is k factorial and gamma of k plus 1. That's really cool. Okay, And now let me just erase these stuffs. So but still, uh, yeah. So this becomes that one, that is I, the infinite series as k goes from 1 to infinity of negative 1 to the k plus 1 over k plus 1 factorial times this integral is k factorial times Riemann zeta of k plus 1. If you look closely, this is k plus 1 factorial and this is k factorial. So if you divide it with that, so this becomes negative 1 to the k plus 1 over only k plus 1. It's not k plus 1 factorial yet, because the rest of the terms are getting cancelled out with k factorial. And then Riemann zeta of k plus 1. Let's write the Riemann zeta function in its most famous way, that is this one, and you have to plug s equals k plus 1, right? So this becomes negative 1 to the k plus 1 over k plus 1 times the sum as n goes from 1 to infinity of 1 over n to the k plus 1. Okay, and now this becomes the double infinite series. One is getting k equals 1 to infinity and the other one is from n equals 1 to infinity of negative 1 to the k plus 1 over k plus 1 times 1 over n to the k plus 1. Okay, and if you would ask me, Aman, then how are we gonna deal with this one? So I'm gonna reply you with, again, the Maclaurin series of ln 1 plus x, and what that says is the infinite sum as k equals 1 to infinity of negative 1 to the k plus 1 over k times x to the k. We have to modify something in this, and then we would get to have that this part is getting vanished with something else, and now we would be writing it, right? Okay, let's do that. Let's just erase all the stuffs on this board. Okay, so if I'm looking at the Maclaurin series of ln 1 plus x, so ln 1 plus 1 over n, and well, keep remember that x should be greater than 0, right? Obviously, because if you take the x less than 0, so this becomes what do you call it? It's invalid, right? It's not valid in logarithm term. So yeah, so let's replace x with 1 over n. So that's gonna give us the sum as k equals 1 to infinity of negative 1 to the k plus 1 over k times 1 over n to the k. When you plug 1 over n on the place of x, right? Okay, so this becomes ln 1 plus 1 over n is, when you write the first term, oh, not like that, no, it's not like that. Begin the infinite series from k equals 0 to infinity instead of 1. So this becomes negative 1 to the k plus 2 over k plus 1 times 1 over n to the k plus 1. So if I'm like negative 1 to the k plus 2 basically means negative 1 to the k plus 1 times negative 1 to the 1. So this becomes negative of negative 1 to the k plus 1, right? So to neutralize this, I'm just going to multiply it with negative sign on the both hand sides. So So that's gonna give us negative of ln of 1 plus 1 over n as n infinite series as k equals 0 to infinity of negative 1 to the k plus 1 over k plus 1 times 1 over n to the k plus 1. Okay, and if I want to begin this infinite series with 1, so I'm just gonna write the first term of this infinite series, so that becomes negative of ln of 1 plus 1 over n. So when you plug k equals 0 in this, so this becomes 1 and this becomes 1, so 0. The first term is 1 over n, and then the rest of the terms, that is k equals 1 to infinity of negative 1 to the k plus 1 over k plus 1 times 1 over n to the k plus 1. Right? Actually, no, it's not plus, it's not positive, it's negative. Because when you plug k equals 0, so this negative 1 to the 1, that is negative 1, right? So yeah, this is what, and if you look closely, this is one of the infinite series is that is going to be replaced it with that. So let me just do it right away. Okay, let me just do it right here. So this becomes, from here you can say that infinite series from k equals 1 to infinity, that is this one, of negative 1 to the k plus 1 over k plus 1 times n to the k plus 1 equals 1 over n, adding 1 over n both the sides. So 1 over n minus ln of 1 plus 1 over n. So this becomes I, the infinite series of n, that is from n equals 1 to infinity, of 1 over n minus ln of 1 plus 1 over n. And finally, this is the infinite series as n equals 1 to infinity of 1 over n minus ln of n plus 1 over n. Right? And this is what our Riemann zeta, I'm really sorry. This is what our Euler's Mascheroni constant. As I told you earlier, I told you we have to prove this infinite series to, like, this is the representation of the Euler Mascheroni constant. That's what we have to prove, and we did that. So yeah, it was great. We used a lot of things like infinite series, Maclaurin series, and that integral representation of Riemann zeta function, right? So yeah, that's a great journey. And yeah, so for this video, thank you so much. Actually, in my area, there's the temperature is quite high. That's why I'm getting sweat. But it's all right. Yeah. Thank you so much for watching this video, guys. Stay tuned for the next video. Bye bye. Let's see you in the next video. Thank you so much.